All right, today we're going to dive into a really cool story from the world of organic chemistry. It's all about a single type of molecule that finds itself at a crossroads, having to make a decision that will completely change its identity. This is a story of choices, pathways, and some pretty amazing transformations.
Okay, let's jump right in. Meet our main character, the halogenoalkane. At its core, it's just a carbon chain with a halogen atom stuck to it. But when this molecule meets another chemical, it comes to a fork in the road. Will it go for substitution and just swap its halogen for something new? Or will it choose elimination, breaking apart to form a double bond? The path it takes all comes down to a fascinating set of rules we're about to uncover.
So to really get a grip on the choices this molecule can make, we've first got to understand the molecule itself. What exactly is a halogenoalkane, and what's the secret to its reactivity?
A halogenoalkane, well, it's pretty much what it sounds like. You take a regular alkane and you swap one or more of its hydrogen atoms for a halogen, fluorine, chlorine, bromine, or iodine. But the real story, the part that makes everything happen, is the bond connecting the carbon and the halogen, what we call the CX bond. See, halogens are way more electronegative than carbon, which means they're kind of like electron bullies. They pull the bonding electrons towards themselves. This creates a polar bond, leaving the carbon atom with a slight positive charge. And that positively charged carbon, it's a big, glowing target, making the whole molecule ready to react.
But here's the thing. Not all of these CX bonds are created equal. As we go down the halogen group in the periodic table, from fluorine to iodine, the atoms themselves get bigger and bigger. That means the bond to the carbon atom gets longer. And what do we know about longer bonds? Well, they're weaker. They take less energy to break. This is the absolute key takeaway. The weaker that bond, the more reactive the halogenoalkane. It's exactly why iodoalkanes are the most reactive of the bunch. That bond is just waiting to snap.
Okay, now the action really begins. Our halogenoalkane, with its reactive polar bond, bumps into another chemical. It is decision time. Is it going to be a simple swap, or a much more dramatic escape?
And this perfectly sums up the whole dilemma. If you react a halogenoalkane with sodium hydroxide that's dissolved in water, an aqueous solution, you get a substitution reaction that makes an alcohol. Simple enough. But, and this is the really wild part, if you take the exact same halogenoalkane and the exact same sodium hydroxide, but this time you dissolve it in alcohol instead, you get a completely different outcome, an elimination reaction which forms an alkene.
So yeah, that's the million-dollar question, isn't it? How can just changing the solvent completely rewrite the story for our molecule? To answer that, we've got to look under the hood at the mechanisms behind each of these paths.
Let's start by following the substitution pathway. It turns out that even down this road, there's another choice to be made. But this time, the decision isn't being dictated by the solvent. It's dictated by the halogenoalkane's own shape.
So, have a look here. On the left, we've got a primary halogenoalkane. That means the carbon that's bonded to the halogen is only attached to one other carbon group. It's pretty uncrowded, right? Now look at the molecule on the right. That's a tertiary halogenoalkane. Here, that carbon is attached to 3 other carbon groups, making it really crowded and bulky. And this structural difference, it changes absolutely everything.
Those uncrowded primary halogenoalkanes, they prefer a pathway that we call SN2. The S is for substitution, the N is for nucleophilic, and that 2 is super important. It tells us that 2 molecules are involved in the key step of the reaction. It's a swift, direct, all-in-one kind of deal.
So here's how it works. A group called a nucleophile, which is just a fancy name for something that's attracted to positive charges, swoops in and attacks that partially positive carbon atom from the back. We actually call it a backside attack. And at the exact same time, the bond to the halogen breaks and the halogen leaves. It's all one single coordinated step. The new bond forms as the old bond breaks, kind of like 2 dancers swapping partners in perfect time.
This diagram shows that beautiful choreography in action. The curly arrows show us how the electron pairs are moving. You can see the nucleophile attacking the carbon, while, simultaneously, the carbon-bromine breaks. There's no intermediate step, no pausing. It's just one fluid transition from the reactant straight to the product.
But what about those crowded tertiary halogenoalkanes? That backside attack just isn't possible. It's physically blocked by all those other groups. They can't do the SN2 dance. So they follow a completely different path, SN1. That 1 tells us that only one molecule is involved in the crucial first step. This is a much more patient 2-step route.
Now, the key difference here is massive. In the first step of an SN1 reaction, nothing attacks. The halogen just leaves. It breaks its bond with the carbon all by itself and takes the electrons with it. This is a slow process. It's the bottleneck of the whole reaction. That's why we call it the rate-determining step.
When the halogen leaves, it creates something new and really important, a carbocation intermediate. This is a carbon atom with a full positive charge. For a bulky tertiary halogenoalkane, this carbocation is actually pretty stable because it's supported by all those surrounding carbon groups. And this stable intermediate is the defining feature of the whole SN1 pathway.
So once that stable carbocation has formed, the second step happens in a flash. The nucleophile, which was just waiting nearby, now sees that full positive charge and is instantly attracted to it. It attacks the carbocation, forms a new bond, and boom, we get our final product. Two very distinct steps, a slow departure, then a fast attack.
So that covers the substitution pathway pretty well. But what about that other choice from the fork in the road? Let's rewind a bit and explore what happens when our molecule decides to go for the great escape, the elimination route.
Elimination is, well, exactly what it sounds like. Instead of swapping one group for another, the molecule just eliminates atoms from its own structure. It loses the halogen, and it also loses a hydrogen atom from an adjacent carbon. The electrons that get left behind then shuffle around to form a new carbon-carbon double bond, creating an alkene.
And this is where the solvent comes back to be the hero of the story. In an alcoholic solution, the hydroxide ion acts as a strong base, not as a nucleophile. This means it's way more interested in grabbing a proton, that nearby hydrogen, than it is in attacking the carbon atom. As it plucks off the hydrogen, a little cascade of electron movement happens, forming the double bond and kicking out the bromide ion. And the result is ethene.
So, now we've seen all the choices and all the pathways. We understand the rules of this whole chemical story. And that means we can go from just being observers to being the directors, controlling the reaction to get the exact product we want.
So it all comes down to this. Chemists have a toolkit to control the outcome. First, there's the structure of the halogenoalkane itself. Is it primary, secondary, or tertiary? That's going to dictate whether it goes SN1 or SN2. Second, you have the reagent's role. Is it going to act as a nucleophile or as a base? And that depends on the third factor, the reaction conditions, specifically the solvent. Aqueous conditions favor substitution, while alcoholic conditions favor elimination. By mastering these three variables, a chemist can guide a molecule to its desired fate.
You see, understanding these pathways isn't just some academic exercise. It's the absolute foundation of organic synthesis. It's how we build everything from new medicines to advanced materials. By understanding the choices one little molecule can make, we can design and create almost any molecule imaginable. So the only question left is, what will you build first?